So we're very happy to have Sergio from MIT to tell us about black holes and non-perturbatively low temperatures.
Awesome. Thank you very much. Super happy to be here. The last time I gave this talk, I got some feedback that I should change the title to black holes and really low temperatures. Because apparently, if you think about a solar mass black hole, temperature would have a factor of 10 to the 10 to the 77. One of them. So it doesn't really matter with which units you work. The number is absurd anyway. So that's kind of what I'll be talking about. And the talk is mostly based on this paper I had recently. But about 1/3 of the talk will also be about work in progress with Rostal, Wayne, and Cornell, and Nico, student at MIT. So let me begin with some words of motivation for studying these absurd low temperatures. There's a qualitative methodology that you encounter when studying the entropy of black holes at very low temperatures. And that's that the entropy, when you don't have supersymmetry at extremality, seems to become negative at some value of the temperature. When you have supersymmetry at extremality, instead you get a continuous curve that goes to some finite value, which is a Beckes-Knight-Hawking entropy. Or if you have into account, you take into account quantum corrections, is some logarithmically corrected Beckes-Knight-Hawking. Now this negativity occurs because of log beta. So these are one loop effects that arise at low temperatures and come from a universal sector governed by the torsion mode, which appears in the throat of near-extreme black holes, pretty much for any kind of black hole you can imagine. And the contribution these gives to the entropy takes this form, some logarithmic factor beta. And so you can see that as we take beta of order e to the S naught, so non-perturbative in S naught, this entropy will become negative. Now you could say, okay, this is a one-loop effect or about higher loops. And the nice thing about this torsion sector is that this one-loop exact, so really perturbatively in 1/S naught, we're doing things correctly. Now how about non-perturbative corrections? And that's that would be a great question. That's the question that I'll be addressing. So what happens with non-perturbative contributions? Do they change that behavior or not? But yeah, this is the general picture. Those terms here are self-leading and we'll not care about them. This has to do with whether there's a gap in the spectrum or not. The important factor that will be relevant in this talk is mostly the log beta. The difference between the BPS or the near BPS case where we have supersymmetry at extremality or we don't is whether this factor of log beta is there or not. So essentially what you find is that this is a formula that you generally get near extremality. When you don't have enough supersymmetry, so for the n=0 or n=1 supertorsion theory, you don't have any BPS states and this constant in front of the logarithm is non-negative. And it's not zero. When you do have BPS states, and that happens when you have a bit more supersymmetry, n=2 or n=4 in the supertorsion theory, that factor goes away and you recover a non-negative entropy. So somehow supersymmetry saves the day for the entropy. But there's a very worrisome behavior of the entropy when we don't have supersymmetry. And whenever we see nonsense in a physical quantity, that's a great place to look at and learn in physics. So that's basically the motivation behind this. So what are the main questions that we want to address, and what are the answers that I kind of promised? I'll just give you a bit of a flavor of what we'll be talking about. So these will show the main questions and the main takeaways. And if you are not interested in either of them after this slide, you can go. Hopefully you are. You're not interested?
No. No, it's the opposite. I'm very interested. I'm just like hoping for those of us who have sort of the vague memory of some of the results that are out there. My recollection is that Luca and friends both understood the spectrum in the supersymmetric case, and also for extremal black holes that are non-supersymmetric and they're very different. And once you, so it's the point that it's not, I would have thought once you know the spectrum, you can just answer this question, the entropy is not going to go negative for the non-supersymmetric ones.
Right, so Luca and friends have done all the actual heavy work. I'm just playing with their results. But so
for the non-supersymmetric case,
Yeah.
we're still doing a path integral that gives a coarse-grained result. And the coarse-grained result is a continuum density of states.
Yeah.
A continuum density of states always has infinite negative entropy at exactly 0 temperature. But you shouldn't trust, right? Because the entropy is 0 if you pick up only once a contribution from one state, right? If you have a continuum of states, you could pick up the contribution from like 0.01 states, right? So the entropy could in principle go negative. But that occurs at non-perturbatively small temperatures. Well, our analysis is trustworthy all the way, even for non-perturbatively small temperatures, as long as those temperatures don't scale like e to the minus the entropy.
which is what I'll be doing.
Which is what it's done.
So that's why it's absolutely low.
And usually what you directly compute really on the gravity side is Z beta. And then from that you can extract the spectrum. But what you see when you go to very low temperatures is that Z beta is becoming smaller than 1, which makes no sense if you have a discrete spectrum behind it.
Yeah, so I'm trying to.
So
before we're talking about black holes, it feels like maybe this is already obvious to everybody, but just like because I haven't thought much about systems that at temperatures this low and what we should expect. What would be?
I'll be discussing.
You're looking for a behavior that's like the near PP, as you know.
I'll be discussing what causes a negativity in the entropy on very general grounds very soon.
I think maybe a good analogy is if you have a particle moving on a line, if you computed the partition function of a particle moving on a line, you'll get answers that are also smaller than 1 at temperatures that are smaller than the density of states in the spectrum, than the inverse density of states.
So negative entropy is the right answer?
It's the right answer for a particle moving on a line. If you put that particle in a box, so you actually look at bound states, at the partition function of bound states, then the entropy goes to 0 and the partition function goes to 1.
There's an if and only if fact that makes that entropy negative. And I'll get to that. And that if and only fact has to do with whether the ground state energy is a delta function, is discrete, or it's smoothed out by even the slightest.
I think I was thrown off by the second question. The second question makes it sound like you're not happy that it's going negative, and something has to make that go away.
Okay, let's get
Just give me the spoiler. I mean, like, it's not going to go away.
It's not going to go away.
Okay, so we have better live with it.
Okay, so the questions. First one is, why does it go negative? We want to understand that, right? To see what is the physics behind it, or whether it's nonsense or not. So one might wonder, maybe we're just missing non-perturbative corrections, which will restore non-negativity. And then you might wonder, are they non-perturbative in S0, or are they doubly non-perturbative in S0? Or maybe there's something different going on, right? And then we also have to understand why or what role supersymmetry plays in changing the quantitative answer. And so the spoiler is, in general, whenever you have an ensemble and you have some averaging of your spectrum, we'll see that what the gravitational path integral generally computes is what is called an annealed entropy. Essentially, you're doing the average in the wrong place. We'll see in detail what this means. And so an annealed entropy must diverge negatively. So it's not an accident. You can think of it as actually a consistency. It's good that it diverges because it's consistent with the story of ensembles and effective gravity. And the only thing that changes that is whether the entropy, or sorry, the energy of the ground state is protected by some mechanism. Supersymmetry will be the mechanism. Degeneracy or gaps are not related, are related only indirectly to this phenomenon. The degeneracy tells you what's the size of the gap, but the degeneracy itself doesn't restore non-negativity, neither does the gap. I'll say more about that. Okay, another question is, okay, so what computes an actual thermodynamic entropy? If this won't behave negatively, that's not very sensible from a physics point of view. So the actual entropy will be, I'll just take the entropy of the theory, if you have an ensemble, and then average that. And that should be non-negative, it's just an average of non-negative quantities. And how do we compute that in gravity? This is called quenched entropy. And in particular, can we characterize the physics that becomes important at such low temperatures? Because whatever plays a role in the quenched calculation in restoring this non-negative answer might also play a role in the annealed entropy, or really in any thermal physics at very low temperatures. And so what we'll find is that in the matrix integral formalism, which is a way of attacking two-dimensional gravity models, we'll find that there's a particular phenomenon known as single eigenvalue instantons, which are not just important at low temperature, they give you the dominant contribution to the entropy, or really to any correlation function or object that depends on C beta. So it's not as usual for instantons, it's not a non-perturbatively suppressed contribution that maybe you can ignore. It's something that in this regime becomes the dominant, and therefore the leading contribution.
Can you say again what you mean by quenched and what is like the average state?
Yeah, I'll be more precise later, but the annealed is average Z beta, and then compute whatever observable you like from that. Whereas quenched is compute whatever observable you like on a theory, and then average that observable. So quenched is do the average at variant, which is what you would do if you want to understand the average behavior of an observable. So in the context of having an ensemble of theories, annealing would be a very naive thing to do. You really want to be quenched. Okay, and then if we get this insight from the matrix integral perspective, we would like to use that to actually learn quantum gravity. Matrices are cool, but not as fun as understanding actual geometries. So what are the gravitational manifestation of these eigenvalue instantons? And do they admit an effective gravity description? And the answer to this will be that there's a precise way of identifying them with a particular type of dynamical graphs, which you're not adding by hand. They're given to you by consistency with the duality of matrix integrals. And this instanton begins to appear, to develop in a somewhat intermediate regime that is non-perturbative, but slightly less non-perturbative. And there, this is work in progress, we'll see that there's a way of reorganizing the usual topological expansion in a way such that there arises an effective description of non-perturbative effects in terms of a modified theory of gravity. This modified theory of gravity is again not ad hoc. We're going to derive it by reorganizing the calculation in a particular way. Okay, so those are all the spoilers. Yeah.
Sorry, before you go on, let me just make sure, like this geometrical understanding, you mean it's more like in the 2D perspective, or you can have it in, say, from higher dimensional perspective?
Great. So at this level, I'm going to be talking about 2D.
Mm-hmm.
The good thing is we are trying to get semi-classical understandings of these non-perturbative results. Meaning, I want something that just doesn't take the form of a complicated sum over geometries, which I don't know how to do in higher dimensions. I want to see if there's an effective description that is just semi-classical.
Okay.
And if I do have that, maybe I do have some hope of going to higher dimensions and understanding semi-classical contributions, which I do know how to
But the earlier one, but the first, let's say, two things are going to be, you're going to assume general matter fields present, higher dimensional, etc.
Well, this one is a matrix integral, so
Oh, sorry.
it'll be zero dimensional.
Well, no, but is it computing something about, I mean, you're talking about black holes. Right?
These are So
black
these are all
holes
motivated by, we're looking at black holes, we're zooming into the very low temperature neutral geometry where there's this particular mode that governs the temperature dependent contribution to the entropy, and that's the Schwarzschild, and this Schwarzschild plays a role in interdimensional JT theory, and there's a
Yeah, but to make sure that the effects aren't washed away by, do you need to assume, do you need to take the strict 2D model to make sure the effects that you're talking about, the very subtle effects, aren't washed away by like matter fields present in the 4D geometry, in the dimensional reduction, or like, or every single thing you're saying is about the black hole, at least the first 2 points, are going to be for general black holes with matter fields around. Again, do they have an altitude for general black holes?
So I don't know if matter effects will contribute similarly or compete, but within the sector I'm going to investigate, I'm giving you the leading order effect. So within this two-dimensional sector,
So you're claiming they are leading order, and
Yes.
those would be subleading.
in the two-dimensional sector, yes. There might be non-perturbative corrections coming from the higher dimensional topologies fluctuating with things of that flavor. And I have no idea what those are.
Yeah, maybe just a comment to Lauren's question. I would say that if you want to just isolate these non-perturbative effects, I might say you need to turn off matter in higher dimension. Like say, for example, this, if you have rotational black hole, this super radiant stuff, that's not non-perturbatively suppressed. But whenever you have matter, that thing exists. So
Yeah.
you need to turn off all of these things just to isolate.
Yeah, I think that's a fair point. Okay, well, let me try to get past the introduction. The whole point of this talk is to explain these comments. So essentially, each of those questions I'll try to address in one part of the talk. So the first one will focus very generally on the idea of what it means to compute entities when we have an ensemble of spectra or an ensemble of Hamiltonians or theories. The second one will focus on the matrix integral analysis of the very low temperature regime, and which is where we see these instanton effects, and from which we can learn about what are the physics at very low temperatures and what are their gravitational avatars. And then we can try to understand those gravitational avatars solely within gravity with the help of the matrix.
Great. So what was your comment about the one loop exactness?
That the Schwarzschild, which is giving you the log beta contribution that
That's what
gives you the negative. Okay. That's one loop exactness.
Okay, so that's why you need to focus on non-perturbative.
Exactly. So higher 1/S0 corrections are not. Okay. So let me begin. Forget about ensembles. Forget about physics in general. Actually. Suppose you just want to do math, and I'm going to give very physical names, but I'm just going to define some objects and give you a thermodynamic fact. So here's spectral density. It's just a function from reals to reals, non-negative ideally. So non-negative could be distributional. So this function could have delta functions. I'm going to define the ground state energy as just the infinity of the support. Again, I'm just giving names to definitions. I'm going to define a potential function as you would usually do in physics, and a thermal entropy, again, as you would usually do in physics. And so now I'm going to make a statement. This object, that I'm calling thermal entropy, is non-negative if and only if this spectral density has a Dirac delta sitting right at the ground state energy with a coefficient that is n greater or equal to 1. Okay. So otherwise, what happens if this is not true, or if this is not true? Well, the limit of the entropy as data goes to infinity, so as I go to 0 temperature, is going to be minus infinity, even only if there's no delta function, so that n is equal to 0. And if it's not equal to 0, then the limit is going to just be going to log n. Okay. Now we can try to read into the physics of this, and that's what we'll do in the next slide. I'm going to ignore that. I made the font small with that purpose in mind. A sketch of the proof is just calculus. But the main takeaway of the statement is that whenever we have thermal entropy, and we see that it's becoming negative at low temperatures, that's a signal, and even only a signal, that we're smearing the ground state energy. So doing anything wrong with the ground state energy causes negativity, and vice versa. So in gravity, we're seeing negativity, that's what we're doing wrong. There's something with the ground state energy.
I don't think that's exactly true. What if your density of states is 0.1 times a delta function? That's not a smearing, but it's still a delta function,
Yeah.
but it has negative entropy, right?
Yeah.
So it's not smooth. It's not an if and only if.
I think it's.
Oh, I see. Okay.
Yeah.
Okay.
You could suspect this minus infinity from just taking n goes to 0 here. The proof is not as trivial because you cannot use the assumptions that you use when n is not 0. But yeah, the picture is.
I agree with the theorem. I don't agree with the bottom box. The bottom box doesn't follow from the theorem. What follows from the theorem is I think a smoothed out ground state energy results in a negativity.
Yeah, I have to add a unit factor at least.
Okay. Yeah.
Sorry. It's what happens when you try to do theorems, it works. But yeah. Yes, so it's smoothed out or coefficient that is 1.
Yeah, but that's a kind of smooth out, right? I mean, you're splitting.
It requires exactly. It requires.
Not continuous splitting.
It requires some being protected and some not.
Dividing single states.
Yeah. Okay.
Can I ask something? Yes. I'm sorry to do it again, any question. In the theory with gravity, I forgot which black holes we were talking about. Like, what is the setting in which I can discuss? So, in order to have a spectrum where I even get to worry about having a continuous spectrum in the ground state, but I need to have like I can't have any kind of IR regulator intuitively. I mean, that's what the idea of the particle online comes from, right? Like, for example, in Minkowski space, I could, in asymptotically flat space, I could discuss things like this. But in asymptotically flat space, I cannot discuss the thermal ensemble in a theory with gravity. It's unstable. What exactly are the black holes at which we can ask, or what's the setting in which we're asking this question?
Sorry, I didn't quite understand. Go ahead. Sorry.
Because this continuum is not coming from an IR effect, right?
Yeah, so
Yes,
maybe that's what I'm missing.
Yeah, so if I
Like,
take an ideal gas,
what it was, but maybe that's not essential.
I could take an ideal gas and make the box infinite, and I would get a continuum, and I would get negative entropys from taking the continuum.
Yeah.
The continuum is just coming from G goes to 0.
Yeah.
The spacing is e to the minus 1 over G, and you're taking G to 0, so you're getting a continuum.
So as I will try to.
Maybe a concrete example is that produces exactly this density of states is Cardy's formula. If you
The
apply.
formula may produce this density states, but
Yeah, but in a real 2D CFT, we expect a discrete spectrum, right?
I guess
So,
I'm just asking from the gravity point of view. Where
Yeah.
am I down in temperature? Are we asymptotically ADS space time?
You could be, yeah, like the example with Cardi formulas was supposed to say that this actually happens for asymptotically ADS-free black holes as, you tune beta at infinity. And you take the Laplace transform of the partition function with finite beta. In the limit when G Newton goes to 0, you see a continuum density of states.
But as I'll argue, this phenomenon in black hole physics is not associated to a continuum limit, it's associated to an average. And do you usually stick to 1 hour? Okay, so one of the lessons or observations in the recent years is that because of the action of wormholes and how they tend to correlate a priori the correlated theories, gravity or the gravitational path integral behaves more like an ensemble, and it's actually something that you can generically argue for whenever you have an effective theory. Effective theory does not capture all the microscopic details, and there's a precise sense in which you can more accurately describe an effective theory as capturing the physics of an ensemble of theories. And so this is what the gravity path integral computes when we are talking about the partition function. It's an average over theories. And when you are computing an average, essentially what goes inside the integral in the Laplace transform is an average of a spectral density. So even if your original spectral densities are all delta functions, are discrete, this average is going to smear them. It's a nice way of understanding what this average spectral density looks like. It's going to look like a peak for each of the eigenvalues. But that peak is now going to be not a discrete delta function. So this is roughly what the average spectral density looks like. And so what are we seeing when we look at the entropy of black holes? We're computing these averages of Z beta and then taking the log outside. So really we are doing this operation. And the object here looks very much continuous because of this smearing. And in particular, when we are near non-BPS black holes, the ground state energy is smeared because every member of the ensemble has a different value of the ground state energy. And that smearing causes one of the conditions of the theory to have a negative entropy. And what happens when we have BPS black hole at extremality is that the energy is protected. It's given by the supercharges. Every member of the ensemble has the same ground state energy. So there's no smearing of the P0, the distribution of the ground state. We have a delta function. That's all we need to have with a coefficient 1, as we said. That's all we need to have a non-negative entropy.
So the integer number of states was also important.
So you're going to get the coefficient, the limit of the spectral density, the limit of the entropy when you're doing annealing is going to be log of the average number of states instead of average of the log. But that's a qualitative difference. Okay, so the point of this is that no matter to what order we're working, since we have an ensemble, even if we are doing the exact computation, and in particular, what the exact computation should give you is a negative entropy at low temperatures, unless we have this mechanism of protecting the ground state energy. And in the near BPS case, I will emphasize we're still computing the wrong quantity. I'll say what the right quantity is, it's the quantum entropy. We're still computing the wrong quantity when there's BPS black hole at extremality, even if the problem is not qualitatively obvious. So we don't have this negative versus non-negative difference, but we do have a temperature-dependent difference.
Sorry, but the temperature-dependent difference is extremely small.
It happens in the gap scale, and it happens, it's a difference between whether the growth off of the extremal limit is polynomial or is exponential.
No, but the extremal entropy is still correct.
The
If you
extremal
take beta
entropy,
to infinity first, then you're still going to correctly recover the extremal entropy. It's just how the states that are above the gap scale contribute.
up to whether the number of states in each member, the number of BPS states varies, which seems like it doesn't. Because that would be a difference between.
Yeah. But that's kind of follows from the fact that the wormholes that contributes with the wormholes when you take the z of beta, with beta going to infinity, all vanish.
Right.
In the supersymmetric case, but not in the non-supersymmetric case.
Okay, yeah, so this is the idea, and so now what I've been saying, the annealed entropy doesn't make sense. Why doesn't it not make sense? Because we're doing the average inside the logarithm. The constant entropy is generally the average entropy. We take the average of the entropys on each of the theories. That involves taking the average of the logarithm. So that's what we actually want to compute if we want access to a thermodynamic quantity. The problem is that, well, in the gravitational path integral, Z and the average are really two sides of the same thing. The GPI does both at once, so we can't separate them like this. But we have a replica trick always at our disposal. And here the replica trick looks like this. We're computing moments of Z. It's similar but very different from the replica trick for the von Neumann entropy. Here the replica number is going to 0, which is a very bizarre limit. And okay, so this is the replica trick we would like to do to compute log of Z gravity. This is just a comment that annealed and quenched agree because of this self-averaging property when beta is small. When beta is large, these are very different, and this is what causes annealed and quenched entropy to differ. The subtlety is that precisely because this analytic continuation is so weird, we have not really been able to compute it in gravity. There's been an attempt in full quantum JT, accounting for all the higher topologies, but the SSS expansion for JT is asymptotic, so that together with the analytic continuation not being unique makes the problem really complicated. So there was an inconclusive result about whether gravity can compute the quenched entropy or whether gravity can restore a non-negative answer. There was another more controlled semi-classical calculation here, which still was left inconclusive because it's hard to, once again, take the full limit here. So kind of the question that remained after these words is, can semi-classical or the gravitational path integral in general actually compute the quenched entropy? Can we actually obtain a thermodynamic entropy that is not negative? And so, well, since we have a different way or a different picture for two-dimensional quantum gravity, which is given in terms of matrices, and in that picture everything is exact, it's not just an asymptotic expansion. We should definitely go into that and see what are the ingredients we actually need and whether those can be captured by gravity. So the goal of the next section is going to be understanding the matrix integral formulation. What are the ingredients we need to understand the very low temperature behavior. And that will matter not only for the quenched entropy, also for the annealed, and also for any correlator of Z beta. Okay, so hopefully I answered most of these questions. This one, actually, you can ask them later. I won't have time to discuss it, but there's a very nice way of understanding the gap quantitatively from the matrix integral and what gives rise to this. We're not going to get into this one. Okay. So let's go to matrix integrals. And let me start by introducing why matrix integrals arise. So what Sad, Schenker, and Sandler showed is that topological expansion, where we sum our topologies in two-dimensional intercube tidal gravity, that's an expansion in e to the minus s naught. And that expansion can be matched onto a similar expansion in a matrix integral, where in the matrix integral side, we have this matrix acting as a Hamiltonian. It's a random matrix, and we are taking an average over these thermal partition functions. And this sign is because on the left-hand side, this is an asymptotic series in e to the -s naught, which holds when that parameter is very small. On the right-hand side, That's an exact expression into the minus epsilon. And these matrices are infinite. They're very large. We're taking a double scalar limit, and that's the defining parameter that remains. Okay, so just what does a general two-dimensional gravity model dual to, or what does a matrix integral dual to the two-dimensional gravity model look like? Basically, an integral over eigenvalues of the matrices. This is the matrix of eigenvalues. A van der Waals, which has some power. The power is determined by symmetries, symplectic, unitary, orthogonal. Those are those parameters here. There's an extra determinant, which tells you about supersymmetry and number of HEP-QIS states. So this parameter on top is related to the number of zero eigenvalues in the ensemble. So supersymmetric ensembles have this factor here. And this is a matrix potential. That's the general structure. And I'm just flashing the general object because what I'll be saying applies to a completely general matrix integral. So we are not going to focus on any particular model. And the van der Waals takes this one. And I'm only showing this because this determinant will show up later. So we can decompose this into a determinant times itself on pure eigenvalues. Okay, now what can we do with this? Compute expectation values in this ensemble. And for that we define the joint probability density function, which is just the full integrand, normalized. So that's the joint PDF of eigenvalues. And we can define smaller endpoint functions of these eigenvalues by just integrating out some of them. So if we integrate out n-1 of them, we get the spectral density. So that's the definition of the average spectral density in a matrix integral. We're just taking this and integrating n-1 of them. Okay, now let's look at the observables we're interested in, Z beta, the ones we want to take with beta going to very large. You can use the permutation symmetry of the endpoint function to just rewrite this integral as 1 over just the spectral density. So you see that Z beta is just an observable that depends on 1-point statistics. So the annealed entropy obeys or is only dependent on 1-point statistics. When we go to a higher moment, this is not going to simplify so much. It's going to depend on n-point statistics. So higher moments capture higher statistics. And if we go all the way to computing the average of a logarithm, well, this depends on all powers. We can extend it, it's not very useful. But the point is the log, or the quenched entropy, which depends on the average of the log, really depends on all the statistics of the ensemble. It's a much more fine-grained observable that we are after. And the replica limit of n goes to 0 by analytic continuation is basically capturing the statistics of the full ensemble. That's why the quenched entropy is not only better behaved, but more interesting as a thermodynamic quantity than just the annealed entropy.
Sorry.
Yeah.
Can you explain this a little better, a little more? It's like if you take the, in what sense the m that goes to 0 limit knows about all powers? Maybe I misunderstood your statement. I thought your statement was that the m to 0 replica trick accesses basically all powers of Z in that sense.
Yeah.
So in what sense that is true?
You're just saying that it's an analytic continuation
Yeah,
that's
yeah.
sensitive to all values of that
Exactly.
thing.
Oh, okay.
I think that's the only statement.
Yeah, that's the same.
Oh, okay. So essentially to the generic for generic m. That's it.
Yeah, and I mean, another way of saying it, the replica trick is just a way of computing this, and this depends on all endpoints.
Okay. Thank you.
Okay, so now that we know what kind of beams we're after, let's look at low temperatures and see what's interesting about them. So traditionally, we treat Z beta as just an observable that we put in the matrix integral. And so we treat the endpoint PDF within the integral as the background, and z beta is just an observable. So we work with a continuum large n saddle for these objects essentially. And that object we saw reduces to one-point functions. So we end up with the leading one-point function of that object, the leading spectral density, and we compute z beta on that. Again, by putting an observable and computing it on some background. But what's happening when we make data very large? Well, that observable is basically back reacting. It's modifying the large n saddle in a very simple way. I have using my integrand is a matrix integral potential times z beta to the n. Let me put it as part of the action, as part of the exponent. And then that's what I have. And then if I take beta very large, this log of these objects is going to pick out the lowest eigenvalue. So I'm going to get a contribution from the minimum of all of these with a beta in front. And if beta scales like m, then this is part of my saddle point approximation equation. So if I compute the equations of motion of my eigenvalues, this term is as important as this one. So the saddle point is changing. And that's the sense in which the observable is back reacting on my theory or on my matrix integral. And I'm going to ignore higher eigenvalues because of these exponential metrics.
Sorry, here you assume that like the minimal eigenvalue is like order 1 far away from the other eigenvalues, right? Like, or say the spacing between the minimum and like the first excited state, like the gap is not parametrically small.
Yeah, so here I'm going to, well, this gets to the discussion I've had very recently. I'm going to assume this behaves like the statistical spacing in the edge of a Gaussian integral, or an Airy edge, where the separation between eigenvalues is n to the minus 2/3. So that's small enough for a beta of order n to make this parameter exponentially suppressed.
Yeah, but like, can you prove that like the weird case I was mentioning is just absent? Like it's just
If the statistics of the edge are not like that, then we have a complication. But I'm going to work with.
I think he's making this ansatz, and
Yeah,
then
yeah,
you're
yeah.
solving the saddle point equation and
That's
confirming that the ansatz is correct.
Yeah, but
That's
what
a
I'm
good
asking
point.
is like, can you prove this answer without
I'll take it.
assuming that's true?
Well, you can do numerics, and I'll show plots. Okay, and well, upon double scaling, this beta going of order n is going to be related to beta going as e to the s naught. So that's precisely the appearance of this modification of the saddle point is precisely the regime where we expect a departure from or non-perturbative effects to change the entropy and to give us the difference between an EO and much. And we also see that the lowest eigenvalue plays an important role. In the same way as in our simple thermodynamic fact, we saw that the lowest eigenvalue was crucial to distinguish a negative versus a non-negative action. So the statistics of the ground state will become very important. Okay, so let's make the observable part of our matrix integral. And so instead of treating it separately, let me make it part of our input function. Then I can define a density of states, spectral density by integrating out n minus 1 of them. Very similar to what I did before, except now the observable is part of my definition. So I'm defining this object. Now it depends on beta. Now I'm going to plot it. Okay? This is the DOE for n equals 5 eigenvalues, n is equal to 1, and I'm going to vary beta. I'm showing the case of n equals 4 because see what happens. When I increase beta, there's a lowest eigenvalue peak that begins to move and goes away from the rest. And at some point when beta is of order n, or here is a little larger, it has completely escaped the rest of the eigenvalues, and the rest n minus 1 eigenvalues have converged to the distribution from 4 eigenvalues. So we see an eigenvalue just single one escaping. The width is 1 over n, so at large n, this is going to become like a delta function. And this is going to converge to the usual Wigner distribution, or the leading spectral density. That's that situation. So, and this in particular is going away by a distance. So the location of this peak is proportional to n beta over n. So that distance is only order 1 when beta is of order n. And the rest of the eigenvalues don't care about beta or n. They just go to the distribution that they would have in an n-1 matrix interval. Okay. Now let's see if we can identify who is given that instant. Sorry. This is called a single eigenvalue instant. Can we identify what gives that within the matrix interval? So let me do one simple thing, which is just rewrite, let's say for n equals 1, this object in terms of what it becomes. So I'm just doing this, expanding this integral, and I get 2 terms. And now I'm going to plot each of them separately. Here I'm plotting them separately. One of them is green, one of them is orange. I'll let you decide which one's which. And the blue is just the sum of the 2. And so when I increase beta, this is what happens. Okay, so one of the terms is becoming the single eigenvalue, and the other term is becoming the old distribution. Do you think which one's which? I think it is. So the single eigenvalue, the one that escapes, is this one. So that term alone is the contribution we want. Why do we want it? Because this only eigenvalue, which is captured by that term alone, actually gives the leading contribution to Z beta. So it's not just some other contribution to this expression. It is the leading contribution when beta becomes large. So if you want to calculate Z beta, not even just the log of Z beta or any other moment, if you just want to compute the partition function at very large beta, you have to compute this term. And it doesn't really care about the n-1 others. It's goes on its own path. So that single eigenvalue instanton is what we are after for very low temperatures. And very nicely, we can treat it on shell. In a matrix integral, we can write this object, the spectral density, in terms of the effective potential that that eigenvalue feels. And I'm going to give you the expression here. And the point is that we have the following series of approximations, which you can justify. When computing this integral, let me write it. This is an equality from the definition we came up with before. This is integrating n-1, and then I integrate the other one, so I get the object I want. In this expression, I'm throwing away the non-instanton part. I'm only keeping the one that I've told you is the leading one, and writing it as this. So the effective potential and this over there. Now I can evaluate the effective potential on the leading spectral density of n-1 eigenvalues. The n-1 we're just tending to their own distribution, and to leading order I can just evaluate the leading effective potential. And that gives me an approximation for what is the potential that this single eigenvalue feels. And then I'm going to do another saddle point approximation for the location of that eigenvalue. And so that gives me this, where the location of this eigenvalue is determined by its equation of function, which is just this one.
So this rho n beta, so when you compute C of beta to the n, it's like you have m rows, right?
You have n rows. Basically, yeah.
Are we assuming factorization or something?
Sorry.
Are we assuming there's some factorization? Look, what is
This
this?
is not power. Sorry, it's this definition. This definition. This definition. So it's just a full integral. It's true it's going to depend on m copies of rho.
Yeah.
But I'm not writing it out.
I see. So you're using the fact that it only depends on the leading eigenvalue, like the
Yeah, that's what comes in here. Yeah, and that comes from me telling you that this term is the only one. Okay, so we have this approximation where we are treating the n-1 eigenvalues that stay together on the cut to lead in order, so it becomes a compact cut on an interval. And we're also treating the eigenvalue that skips classically. And that gives us an action. This object here is the action of the single eigenvalue symptom. And what you find, and I'm not going to show it because I want to say other things, is that if you account for this eigenvalue symptom and do the replica trick, you get a quenched entropy which is non-negative, and that's great because we solved the quantitative issue. You also find that the annealed entropy is modified. So in other words, the annealed entropy that diverges negatively now behaves differently. And what happens is that it actually diverges even faster. So the instanton is important for low temperature physics for anything, not just the quantity calculation. And in the case of in the BPS case, it modifies the behavior within the gap. So it doesn't change the strip limit, but it plays a role in very low temperatures. And so we can define the on-shell action basically from the previous slide, and you can think of it as a Legendre transform of the effective potential. Because we are just computing the infimum here, or maybe the supremum if you change the sign. So the instanton action is essentially a Legendre transform of the effective potential of the matrix integral. This is a very simple thing to compute. If you give me a matrix integral, I can compute the instanton action very easily. So we can check if this treatment satisfies any results in the literature. And so there's an old result about 1/2 BPS Wilson loops, which are dual to unitary matrix integrals, where they obtain a result like this with completely different methods. And in this case, we obtain it this way. And this is the action for the instanton, and it matches precisely the action they get. And the beautiful thing is that this old result has also a holographic picture, where this action is actually the action of a D3 brane that is dual to multiply ramp Wilson loop. So you have lots of strings interacting, and the effective description that arises is that of the dynamics of a D3 brane. And the action of that D3 brane is this, the single eigenvalue system. There's another for JT, we also have to check. This is the action for the JT case of the instanton. It's only well defined for large beta, but not too large. And this has to do with the instabilities of JT. But I'm not going up that anymore. And this match is also a calculation by Okuyama, where he looks at an expansion of the free energy. And so this is the leading order of that expansion of the free energy. So this procedure of instantons really is working. Okay. How long do we have?
How much do you?
I just wondered whether I want to rush the last part or make it
Half rush.
10 minutes?
Yeah.
Okay. Very good. Then, okay, so I've given you the whole matrix integral picture, the importance of these instantons. What about gravity? Can we identify those instantons in gravity? What are they? So let me rewrite. You saw that spectral density, that was the single eigenvalue, can be written in terms of the effective potential. And that object, if I write it this way and define this object has the matrix potential there, and the determinant, that determinant that came out of the Vandermonde when I extracted n-1 and I kept the determinant. So this object is what is called in Luttel theory an FCCT brane operator. And it's called an FCCT brane operator because it can be associated to a specific type of boundary conditions. And on the gravity side, that's going to give us some insight as to, well, the eigenvalue instanton is precisely related to a particular type of break effect. In JT gravity, this beta is for the unitary ensemble is 2. So the expression that we had before for the single eigenvalue instanton is just this. It has 2 FCCT branes. Now, what are 2 FCCT branes? They're a CC brane. And that's just another name for, that appears in Luttel, And a ZZ brain, you can think of just as a extremum of the effective potential. Except in that case, it's not just extremum of the effective potential. The equation of motion we had also had beta. So you can think of extremizing this as having an extremum of the effective potential combined with the contribution from beta. So it's a particular type of ZZ brain effect on a modified potential due to the large temperature, large beta. And then you can do some gymnastics with the determinant to actually understand why this object is called brains. So the determinant, you can raise to the exponent as a traceable logarithm. Now we have a trace, and single traces can be understood in gravity as boundary conditions. We can expand this, and we have correlators of single trace operators. And those are correlation functions of many boundaries. And if I have these correlation functions, including both connected and disconnected things, I can also raise that to an exponential in terms of just the connected parts. So we can rewrite this brain operator as the exponential of some type of open gravity theory, where what I mean is that this object is summing over all possible numbers of boundaries, and each of those will have all possible genus. So it's a type of gravity theory where I have all genus contributions and I also have all possible numbers of boundaries. And so the instanton effect we're after is actually the first term here, the single connected brain, so a disk, and to genus 0. So it's a disk. It's a disk with these boundary conditions. And with lambda, the boundary condition eigenvalue fixed dynamically by beta. So the equation of motion here fixes this lambda, the FCZT brain operator, to take some value. That's kind of the picture of how brains come into play a role here. Now, can we understand this transition from just, you had JT, you had some Z beta boundary condition, and you were summing over topologies, and then suddenly I'm telling you that at very low temperatures, we go to an expansion in the exponent with open boundary conditions, with brains. Can we understand that more geometrically? What's happening? Given that we have a lot of control over the genus expansion, so it would be beautiful to have a more geometric picture of this change of regime. So the intuition is the genus expansion that we are used to by such increments temporary. That makes sense for high temperature, or rather not too low temperature. Whenever beta becomes of order e to the 2/3 S naught, it breaks down. It breaks down because all genus contributes the same. And it was an asymptotic expansion, so not much to learn from it. To see these more explicitly, this is the genus expansion. This is the parameter that suppresses higher genus. But you actually realize that these terms at higher genus are polynomials in beta of a particular degree. And this degree is basically like this factor. So essentially these polynomials are becoming large as beta goes large. So there's a competition between beta and e to the S naught. And the actual effective parameter of the genus expansion is a combination of the two. So that's what tells you why this genus expansion goes wrong at low temperatures. And so it's bad news for the regime we're interested in, which is even lower temperatures than this. Can we fix that? So it turns out you can expand those polynomials and dissect what they depend on. Those polynomials are given by valid figures on volumes, and those are given by Sansor intersection numbers in moduli space. And the upshot is that if you dissect all of those terms, you get a double series. So I'm writing out the polynomials, basically. And when I write out the polynomials, I get this double series, which is the genus, but also an L that appears on beta. And that's great, because now we have extracted all the beta dependence, and we can easily identify exactly which are the smaller terms when beta is large. And here you see that what we want a large beta is to keep L equals 0. And when we keep L equals 0, everything else contributes at the same order. So all genus contribute the same. This lambda is the effective parameter that is order 1 in a particular limit of the 2/3 S naught. So these reorganization tells us what is the leading term at large beta. And the beautiful thing is that the sum there is convergent. So the genus sum is fully convergent. You don't even have to borrow every sum or do anything fancy. The genus sum is completely convergent at every order in N. So these reorganization here, these ones are full genus sums, are all fully convergent. And now we've isolated a particular very non-perturbatively low temperature behavior as the one by the L equals 0 case, which is some sum over genus of a particular type of intersection numbers.
So can you say what lambda was again?
Lambda is these new effective parameters,
Oh, I see.
which is order 1. I'm going to consider this particular limit of beta of order into 2/3 system. So it's very large, non-perturbative, but not too large.
So is this exactly the same mechanism that Yao, Kutov, and Blomart used to recover the plateau? They also redefine a variable, the tau scaling limit that was t times e to the minus s naught, and then they get a convergent expansion once they drop some leading terms in t.
So it's very much the same, except with beta, I need to go to this regime of the 2/3 s naught. If I go past that, the expansion is actually not good. Whereas in the tau scaling in real time, there's a different behavior, and there's some cancellation of terms that causes or allows you to take the real time to be e to the s naught. But the geometries or the intersection numbers that contribute are the same. They're the area limit and they give you the ribbon graphs. So yes, it's the same limit obtained by making the imaginary time large instead of the real time.
Yeah.
And those scale with a 2/3 difference. But yeah, the corner is the same, and the genus convergence is the same. The intersection numbers or the factors for the L equals 0 are known, so you can actually do the genus resummation, and you obtain this answer. So that's the leading answer. That's the result you get in these non-perturbative low temperature limit. And what I'm going to tell you now, briefly, is how you can get that result from gravity. So this is taking us towards these non-perturbatively low temperatures. This limit of L equals 0 corresponds to an area limit, where the Weyl-Petersen volumes don't depend on the kappa class, they don't depend on the Weyl-Petersen volume, symplectic form. They only depend on topological numbers. So it's a topological gravity limit. And so these are the things that contribute at large beta. And these area volumes can be obtained from Weyl-Petersen volumes, the ones for JT, by basically taking the limit of G, the geodesic of the volume. So these are the volume for some genus, one boundary, and the boundary has length G. If I take B to be large, I recover this up there. And when beta is scaled very large, the temperature is very large, I'm effectively causing the geodesics to be large. So I care precisely about this limit of the geodesic of my volume term is very large. And that gives me this area limit. And here's a piece of heuristics for what I'm going to say next. What happens when I make the geodesic of my Riemann surface very large? Any genus inside that surface, any cycles associated to genus will effectively look very small from the perspective of the geodesic boundary. And when the cycles look very small, essentially from far away, they look like thin tubes that are going to pinch off. And when something pinches off, what I get, or an effective description of that, is a cusp. It's a defect with 0 in it, or a 2 pi defect. And so with that piece of intuition in mind, what you find is that you can actually formalize it and look at the actual explicit ways of writing these volumes in terms of what are known as ribbon graphs by consensus. And what you find is that essentially every genus in the Weyl-Petersen volume, in the limit that the geodesic is large, contributes 3 cusps. And so we get this identity which tells you that high genus surface with a single boundary that is very large to leading order is the same as a zero genus boundary, sorry, a zero genus surface, meaning like a disk, with 3G cusps in it. So all of these genus that are populating our geometry have pinched off and are giving us just a surface that is a disk with a bunch of cusps.
Sorry, just to confirm, like in the, I can never remember, firewall or wormhole paper by Kevin and Thomas, like they also discuss this ribbon graph.
Yeah.
I'm thinking is that exactly the same?
These ribbon graphs are the same. They're discussed in...
Like they're having the G equals 1 case, but like I'm just trying to make sure if, yeah, they're exactly the same.
These are described also in the paper that Luca mentioned. They're also described in the convergent genus sum for the plateau. So they arise in different contexts from what you're thinking.
Sorry, I think I don't have a good intuition for what's happening. How did you get free G? Wouldn't you, like, let's say that we have G equals 1, that's 4, so free additional cusps?
Free cusps.
Yeah, how do you get free cusps by making one cycle small?
That's the heuristic. But then you look at the actual graph, and it doesn't quite look like that. But you look at the actual ribbon graph, and the pinch-up limit essentially corresponds to vertices getting deleted. Those vertices are the trivalent vertices of ribbon graphs, which are associated to pair of paths decompositions. So you can probably associate the pinch-up of the pairs of paths corresponding to these vertices of the ribbon graph to the cusps that arise, and that's how the...
But that will give you the wrong number of cusps, right?
No, it would give you 3.
Give you 3? Okay.
This is something that we've been working on in the last couple of weeks, so I'm super happy to draw a graph later for you to explain the 3D. But so again, high genus, large beta, equal to lots of cusps. And lots of cusps with a combinatorial factor, which in particular the G factorial tells you that you can interpret them as indistinguishable, just like in a Gaussian cusps. So you can actually reinterpret these large beta contribution summing over genus as a sum over a number of cusps. And it's a class of cusps, which in JT we can describe by inserting an operator that looks like this. The 3 is for the 3 cusps. This factor is like the insertion of a cusp. And when you do the sum over all possible cusps, this exponentiates. And so it gives you an action which is JT plus a deformation. So it's a theory of JT with a deformed potential, which has been studied. People have studied what happens when you deform JT by a gas. And you can work out what is the leading answer that you get in this modified theory. And it checks out. You get precisely the contribution that we claimed the leading order genus sum would give. Except here, we're reproducing it with a single contribution in a modified theory. So in other words, just the disk on this modified theory gives you the very non-perturbative result of summing over all possible genus at large beta.
But the disk on the modified theory gives you the wrong result at small enough beta.
Yeah.
So it's not quite that the theories are just the same at large temperature. Sorry, at low temperature.
No. So here, beta is still order to the system.
Yeah.
If you make it small, not very, doesn't really matter. But the point is there's an emergent effective gravity description for these non-perturbatively low temperature limit. Okay, and I think I'm gonna end there. Hopefully that answers the picture I gave here. And then I'll just conclude with a few open questions. It's not within the 10 limits I promised. So I'll just go through them very quickly. We got this area limit effective theory with a modified potential. Can we go beyond that limit? what if the cusps interact? Can we reproduce the subleading corrections to that area limit? What happens to higher topologies in this modified theory? The cusp theory gives you an edge on the spectrum that is shifted. Instead of being a 0, as in JT, it's shifted with an energy to an energy that is smaller. This is small in the limit we're considering, but it's the first signal that there's an eigenvalue or something moving to lower energies. And in particular, this value, which is the new edge of the spectrum, is actually precisely the location that then you go and find for the lowest eigenvalue when you go to the very, very low temperature limit, and you actually have a single eigenvalue instant on scale. So in this intermediate regime, you're just shifting the edge, and when you go to even lower temperatures, there's one eigenvalue escapes and the rest recede to their original location. And then can we go to the extreme low temperature limit with an effective gravity description? Can we go from these cusps, gas of cusp, to actually the full brane description? How does the geometry open up to branes? We would like to gather a better understanding of that, probably with some word volume description of the branes. And we can try to gather some intuition from the D3 brane case, which describes the strip limit. And then some various questions about, well, can we go back to the higher dimensional black hole? We've had this topological sum reinterpreted as cusps and a single effective theory with a single contribution. So that might tell us something about how is the quantum geometry of the higher dimensional black hole modified near the horizon. How is it related to the tau scaling limit of real time? And what about replica bubbles? What does this instanton or these higher replica brane contributions look like when we have more than just any? I'm way over time, so thank you.
Questions for Sergio?
Besides the fact that this modified Lindenthal theory works out for these temperatures that are E to the 2s not over 3, so it's a nice calculation thing, but is there any intrinsically interesting like paradox or issue that you would, could you have started your talk saying, well, at temperature E to the 2s not over 3, this happens, and we got to figure out how to like cure this by adding corrections or
Wait, cure?
like you started
Negativity of change.
yeah, the negativity with that particular thing is a need to be S naught beta, but this given that some calculation, niceness happens for this amount of beta, is there some like problem that arises that you can resolve?
Yeah, actually the negativity starts to happen at E to the 2/3.
Oh, it does. Oh, sorry.
Yeah.
Because of the 1 over beta to a 3
Yeah,
halves.
so the factor in front of the law is a 3 halves. I was just at the beginning not caring about the 3 halves, but yeah.
Oh, I see. So then, why do you want to go to beta over the S naught?
So that's because from the matrix integral perspective, that's when you have a new saddle point regime with a single
Okay,
eigenvalue.
so you're saying that was like overkill for solving the negativity issue?
It was overkill, but it was a regime that meets the saddle point approximation.
Okay.
So
Essentially,
essentially, these 2/3 is an intermediate universal regime where the single eigenvalue instanton and the rest of the cut contribute equally. And you're zooming into the statistics of the edge to the point that you only care about the area edge. So you're not seeing sort of the rest of the eigenvalues, and you're not seeing many details about the theory. If you go to the stronger limit, now you're dependent on more limit, more statistics, so it's not just area. This becomes non-universal again, but has a saddle point approximation. So our hope is to also find an effective description for the stronger limit that is dual to just the eigenvalue instanton. But so far, we've only zoomed into 2/3.
But in some sense, that is a more semi-classical regime from the matrix integral perspective, because you are finding a new saddle, an actual saddle for the matrix integral. The typical saddle for the matrix integral just corresponds to the disk answer, which is the standard black hole. The one eigenvalue instanton is a new saddle in the matrix integral, which presumably also corresponds to some new on-shell geometry.
Right. And that's what we hope to find.
That's where you say brain, because that's typically associated to brains, so the single values.
Yeah, so there's a sense in which these brains are understood, but not as on-shell geometries, or as leading solutions to some action. And so that second sense is what we would hope to find. But the insight comes from that expansion of the determinant, which is the single trace. And so intuitively it should be just with the appropriate boundary conditions. But it's not, the answer is not as direct when you think about an action to response.
Yeah, maybe a little bit detailed question. So if you consider this BPS, near BPS black holes where you already have a spike, like in the spectrum, you already have a delta function. If you still go to very low temperature, do you see like the continuum part of the spectrum, like, you know, also kind of emit a single, single eigenvalue instanton from the action?
Yeah, so in the BPS case, this single eigenvalue travels along the gap.
Yeah, so then it's more like you have a spike of BPS states, you have the continuum states as 0, and then there's somewhere in the middle.
Right, so there's an eigenvalue which moves along the gap, and that's why the thermal behavior of any quantity is actually modified on the gap scales, because this instanton can travel along the gap. It never goes past the delta function, and that's, you can work
yeah,
with the
that's
equations.
BPS, yes, perfect.
Yeah.
So you mean in the limit where beta scales is e to the 2/3 S0 or
Beta e to the S0.
Why is there an instanton in that case? I would have
The BPS
expected,
scale.
yeah, like
So-
the lowest eigenvalues are all at 0.
Yeah, no, so the thing is, in the matrix interval description of the supersymmetric case, essentially is a construction where the random matrix is the supercharge, and it's a rectangular matrix. And you make the Hamiltonian out of transposes of this rectangular matrix, so they have a definite number of 0 eigenvalues, and those stay at 0. What the matrix integral describes is the statistics of this non-zero singular lines, or this non-zero eigenvalues. So the matrix integral, where the dynamical eigenvalues are the non-zero ones. And so within the non-zero ones, you see this instanton.
But when the thing you inserted was like Z of beta, right?
Yeah.
And Z of beta is highly dominated by the 0 eigenvalues. Like there's no special pressure for the lowest in the continuum to leave the continuum, right?
No, so the lowest just gets out of the integral. It's just a constant in front. But you still have the integral.
Can I make a small comment?
Yeah.
Maybe? I just wanted to maybe clarify something that you said, which is that that this instanton captured the statistics of the minimal eigenvalue. I don't think that's actually true.
Okay.
I think you're technically seeing these instantons capture contributions from tails of the matrix integral. I don't think most of your matrices in your ensemble don't have an eigenvalue that's that low as lambda instanton. The only reason you're seeing something that moves so much from the rest of the spectrum is because when you insert e to the minus trace e to the minus beta h, you're putting a lot of weight on the matrices that have very, very low eigenvalues. So in some sense, with your calculations, you're really just probing the outliers. of the matrix ensemble.
Right. And yeah, so indeed, what the instanton captures is really the tail, and it enhances the lowest parts of that tail. So yes, I agree. It's
Yeah, maybe to just give some math to it. If you computed expectation value of lambda min, it would be very different than the log of your expectation value of e to the minus beta lambda.
right.
Even if when you term beta very large.
Yeah, totally agree.
Any other questions? Okay, now let's thank Sergio.